Dames en heren, welkom bij de designpresentatie van Project March. Hartelijk dank voor uw komst. Ladies and gentlemen, welcome to the design presentation of Project March. Thank you for joining us tonight. De presentatie gaat zo beginnen. Neemt u plaats op een van de marchblauwe stoelen in de zaal, zet uw telefoon op stil, maar vooral geniet van de show. The presentation is about to begin. Please take a seat, put your phone on silent mode, but more importantly, enjoy the show.
"7:30, my alarm goes off. It's time to get out of bed and start my day. I hop into the shower, turn on the water, brush my teeth, and put on my day cream. I'm late, of course. So I run downstairs, grab some bread, coffee, eat, drink as fast as I can, and hop on my bike to get in time at work. My name is Marilena Dortland, and I'm the team manager of Project March. During my morning routine, I'm dynamic, flexible, and I rely on every part of my body to do exactly as I want. I accelerate when needed, slow down to prevent falling down the stairs. I walk and use my hands at the same time, probably do some talking as well. See, I don't think about my actions, but I trust my body to do what I expect it to do. Having faith in your body is something natural for most of us. With our body, we sense our surroundings. Our nervous system translates the things we touch to our brain. When we use our feet to feel if the water of the shower is comfortable, we automatically pull back when it's way too hot. When we stop our little toe, our whole body knows, ouch, that hurts. And even when we have the feeling we lose control for a second, for example, when we run downstairs a little bit too fast, we still have the faith that our body will catch itself and bring it back in balance. Not everyone can trust their body the way I just described. Paraplegics can't. Paraplegics are people with the inability to voluntarily move the lower parts of their body caused by a spinal cord injury. A spinal cord injury entails that the nerves are damaged at a certain height of the spinal cord, causing to have no motor nor sensory function below height of injury at all. Therefore, these people are wheelchair-bound. In the Netherlands only, there are about 8,000 people with a spinal cord injury. Around the world, that number adds up to 1.8 million people. Being wheelchair-bound affects the lives of these people drastically. The hopping into the shower will take more preparation time. Running downstairs is not really an option anymore, and cycling will have to be done with your arms. But these are only visible examples. Next to this, it has a huge impact on both the physical and mental health. Muscles and bones are weakened. Blood flow becomes less active, and therefore the cardiovascular health worsens. Something we don't think about as well is the feeling that everybody always looks down on you in the most literal meaning. Improving the lives of people with a spinal cord injury has been the driving force for the members of Project March. Now, the key question is, of course, how do we do this? Since 2015, we have been building exoskeletons. An exoskeleton can be explained as motorized robotic legs attached to the outside of the body. It enables the user to stand up and walk again. It's an advanced piece of technology, and to make it understandable, I will explain it on basis of the human body. The bones are featured by the frame. This carries both the weight of the exoskeleton and the user. The muscles are mimicked by the motors. To make sure we can move fluently, we make use of robotic power joints to make sure we can bend our legs. All right, these three elements together would enable movement, but walking an exoskeleton like this would be a complete disaster since we have no control. So, the brain of the exoskeleton is featured by the software, which determines when, where, and how to move. Just like our own body, everything has to be connected by a nervous system. So we make use of electronics to connect all the pieces together and let the exoskeleton do exactly as we want. Now we're almost there. This exoskeleton supports the user and enables him to move. To direct the exo, we make use of an input device, and we use our crutches to make sure we don't fall over. On the 8th of August, the 8th team of Project March entered the Dream Hall. 27 students with 11 study backgrounds strong, all believing in a vision set 8 years ago. To improve the lives of people with a spinal cord injury by pushing exoskeleton technology. Divided over 9 departments, we make sure to innovate, build, and test a completely new exoskeleton in just 1 year. Over the last 7 years, that looked like this. By using the exoskeleton and crutches, we could race, tackle stairs, uneven terrain, and even the outside world. We, as students, pushed the limits, but we didn't do this alone. Let me introduce you to our 28th team member, the most important team member, our pilot, Koen van Zeeland. Koen is a 36-year-old, excuse me Koen, young, well-known TV personality, known from first dates, and has been involved with the project for the last 3 years. He knows the project better than anyone and is probably one of the most experienced exoskeleton users in the Netherlands. By having been part of a rehabilitation program using an exoskeleton, he got acquainted with the technology and experienced again what it was like to move. Together with Project March, he has been pushing the boundaries, and thanks to his strong-minded perseverance and his ability to go for an extra mile, we have made incredible progress. 7 years of innovation already done. 7 years of making most of the obstacles in my morning routine already possible. The tight cooperation between exo, pilot, and crutches enabled standing, walking, tackling stairs, and dynamic movement. It's incredible what we have already accomplished, but there's still one next step to take. A step towards walking without any limitations. A step towards complete freedom.
En een van de andere wensen die ik heel graag zou hebben, maar waarschijnlijk alle mensen die dus ook een exoskelet dragen, is dat je die krukken niet meer nodig hebt.
Of course, that's the dream. Everyone wants an exoskeleton without crutches, but technology is not quite there yet.
Als ik de vrijheid zou kunnen voelen zonder krukken, ik denk dat ik daar stiekem wel een traantje op zou moeten laten, als ik het zo mag zeggen. Dat zal wel iets maken dat ik gewoon echt, dan geef je iemand echt een vrijheid terug. Nu is het nog steeds, je doet er lichamelijk iets mee, je maakt het voor mensen, hun lichaam wordt er gewoon wat beter van. Maar dan maak je geestelijk ook een hoop los, denk ik.
Achter mij zie je ook een foto waar ik nog echt met 2 krukken sta. Als je die krukken zou weg kunnen strepen.
De wens om zometeen geen krukken meer te hebben. Dit is zo'n gigantische uitdaging dat het niet lukt in een jaartje. Dit moet een plan zijn dat je over meerdere jaren hebt.
Balancing an exoskeleton with a person that's freely moving his upper body proves to be pretty challenging.
Ja, dat is het eerste eigenlijk wat je veranderd zou willen zien aan zo'n exoskelet. Dat je gewoon weer kan lopen zonder eigenlijk een hulpmiddel. Dat is ook het moeilijkste voor een piloot, dat in balans blijven.
a self-balancing exoskeleton. Something I wouldn't even dare to dream of in the first place. For the first time ever, our pilot Koen will be able to throw away his crutches and walk again. With being able to walk free-handed, the full potential of our exoskeleton will finally be unlocked. Ladies and gentlemen, my name is Gunnar Zwart, and I am the project manager of Project March. So let me describe to you how we came to this very ambitious team goal. Over the past 7 years, we have shown you what is possible in exoskeleton technology. 7 highly ambitious teams have proven that with dedication, collaboration, and persistence, the impossible can become a reality. Starting with March 1, a team which has to start everything from scratch. With our 8 degrees of freedom, certainly one of the most flexible exoskeletons at that moment, able to follow the movements of the human motion precisely. With the start of this movement, March 1 formed the hope for many paraplegics on a future without their wheelchair. Moving on to March 2, we simplified the exoskeleton, thereby only focusing on the knee and hip joint. March 2 made it possible to stand up straight next to your partner and look them in the eyes again. Then, with March 3, a new joint was added in the ankle. This ankle joint resulted in an even more accurate heel strike, enabling us to tackle stairs, slanted paths, and even the obstacles Marilene mentioned in her morning routine. March 3 was also the team who won the Cybathlon Experience of 2018, a worldwide race for bionic athletes. So quickly after this, another joint was added in the hip, in the March 4. This hip joint made it possible to walk sideways while keeping the flexibility of the current joints intact. The same exoskeleton design was then used in March 5 to compete in the Cybathlon, focusing on reliability and splash-proofness. So, from there on, March 6 enabled us to walk outside in the city of Delft. For the first time ever, walking seamlessly on various terrains outside was possible. And then last year, March 7, they achieved a fully dynamic, automatically generated walk, or a gait, as we would say. With dynamic walking, the exoskeleton will automatically think about the next most optimal foot placement in order to walk without any disturbances. And next to that, the first steps were made by introducing brain control. March 7 made it possible to start walking just by thinking about it. Over the past 7 years, people with a spinal cord injury went from a seated, wheelchair-bound position to eye-level interactions with their environment again. After all, I think it's safe to say that these innovations changed the world for paraplegics tremendously. With these innovations, it is possible to stand up straight next to your partner, walk with them on various terrains, and initiate this gait with your mind. However, although all these innovations brought an exceptional amount of freedom to our pilots, they were in all March exoskeletons bound to the use of crutches. Our pilots weren't able to use their hands while walking. So that's why this year we would like to take the next crucial step in exoskeleton innovation: balance. So at the beginning of the year, we set this goal for ourselves. Project March 8 will enable a paraplegic to successfully walk self-balanced. Looking back at the innovations I just described to you, finding a new challenge seemed quite difficult, as so much had already been achieved over the past 7 years. However, the balancing challenge had been mentioned since March 1, but was actually never really touched upon. So you may ask, why is this? Why is especially balance such a hard thing to achieve? To answer this question, I ask you all to think back at the first moments you tried to ride a bike when you were young. The art of balancing is something which consists of many neural controlling mechanisms which have to work perfect, all the time, at the same time. Something that is partly inherent within the capacities of our brain and partly has to be learned by just doing it. The first moments on your bike are, of course, the most difficult. You need to accelerate yourself with your feet and place them on the pedals. Then maintaining your speed by executing force on the pedals, all while holding your balance by compensating with your torso. While doing all of this, you also have to steer in the right direction and, of course, keep an eye on the road. All of these movements eventually need to be fixed into neurological patterns which can be performed effortlessly. So, if we want to achieve balance within our exoskeleton, we need exactly these neural controlling mechanisms to mimic by using advanced custom algorithms. All of our sensor data needs to be integrated in order to generate a stable gait. And also on a hardware level, if we want to control the movement of our joints as accurately as possible, we need to have fast joints which are able to sense torque. And besides that, the communication protocol needs to be extremely fast and reliable. But not only the exoskeleton itself needs to be changed. Together with our physiotherapist, we need to prepare a Koen, or extremely experienced pilot, for the physical challenges that a self-balanced walk has. All of the challenges I just mentioned are in fact big enough to be tackled by themselves in just 1 year. In order to achieve balance, we need to tackle all of these challenges at once. Since the start of the year, we have been dedicated to this very ambitious team goal. We have worked incredibly hard for 26 weeks to integrate all of these challenges into one final design. Today, I am so proud to present to you the design of the Project March 8 self-balancing exoskeleton.
Isn't it amazing? I've been watching this on replay for weeks. Everyone, I'm so thankful to be standing before you today. My name is Wendel Posma, and I'm the Chief Engineer of March VIII. To introduce you to the EXO, I'd like to paint you a picture of my perfect afternoon. I can quickly go home during my lunch break. After a tough morning, I'm making my habit to cycle home to get out any excess energy. And when I get home, I greet my cat, who's usually grumpy enough to meow once. After some lunch, my girlfriend and I decided to take a walk in the park just outside of Delft. Like some romantic movie, we can cheesily hold hands as we walk under the trees. See, it already puts a smile on my face. Today, we are presenting a unique design to you, that of a self-balancing exoskeleton. But seeing March VIII also begs the question, how can this exoskeleton finally balance? And why can most other exoskeletons around the globe not do this? I will try to answer these questions and guide you through the workings of the March VIII. It all starts at the top, or what we call the backpack. Inside it, you'll find the brains of our exoskeleton. The main computer and other electronics are housed here. To realize balance, we have upgraded these components to operate at higher speeds, speeds that we can use to react even quicker to our changing environment. We've also made design changes to the backpack. By making it thinner and higher, it tailors better to the upper body of the pilot. It also means we can more easily balance the exoskeleton as our center of mass moves closer to the pilot. Our exoskeleton can take over the movement of the human muscles using 8 strong motors. 2 in the left hip, 2 in the right hip, 2 in the knees, and 2 in the ankles. To the sides of the backpack are our first 2 motors, or joints as we like to call them. These are the linear joints, and they help the pilot move his hips from side to side. You can also find them in the ankle, moving the feet of the pilot. This year's linear joints have been heavily redesigned. They're now twice as fast and stronger to more easily handle extreme scenarios like falling or tripping over obstacles. The biggest change is the new spindle. Similar to the transmission of a car, the spindle transfers the energy of the motor to motion. This part is now precision manufactured with the help of our partners, meaning it can best mimic the sideways movement, the abduction and the adduction of the human hip. Moving down towards the upper leg of the exoskeleton, you will find the biggest motors that March has to offer. These are the rotational joints, and they've been custom made in March for many years now. We are very proud to build upon the design of March alumni again this year. We did implement one change though, torque sensing. Sensors that can measure the force the motor is putting out. These sensors have been added to both the rotational joints and the linear joints. Implementing torque sensors is essential for creating a self-balancing exoskeleton. Previous March exoskeletons have all used sensors that send the motors to a position. With torque sensors, you can instead actuate the motors based on their power. And due to the high accuracy of these sensors, we can make very small corrections close to 1/10 of centimeters. You can imagine that making these small corrections is essential for balancing. Imagine me cycling back home on my aforementioned ideal lunch. Since I'm not using training wheels on my bike anymore, it's up to my brain and my muscles to keep my bike straight. I don't do this with huge steering movements left and right, swerving all over the bike lane, but instead make very small corrections in the steering wheel I myself don't even realize after cycling for almost 20 years. I make these adjustments based on the forces I feel in the steering wheel, and it is these forces that we want to measure in our exoskeleton. And that's precisely what our new torque sensors can do. All 8 of the torque sensors are custom made. On top of the linear joints, we have placed torque sensors named load cells. These load cells move parallel to the joint, and it's because they move with the joint that they can accurately measure the force the motor is putting out. The rotational joints have similar designs, but together with partners, we've managed to integrate that same sensor into the housing of the joint, so you won't be able to see it from the outside. The sensor can measure very small deformations in the metal parts around the joint here, deformations close to 1/10 of millimeters. And with this data, our software can determine the force the motor is putting out. Looking at the rest of the exoskeleton, there's a lot we actually cannot see. Underneath our new bio-inspired covers and around the motor parts I just touched upon is the frame of the exoskeleton. This aluminium structure carries all the loads acting on the exo, and it holds all our components in place. Our engineers are always working hard on optimizing these unsung heroes of the exoskeleton. All of our parts have been designed for manufacturing. And by being the first March year to complete a full force analysis on the entire frame, our parts are now more easy to machine, simpler, and as lightweight as possible. Since January already, our engineers are working hard in a DreamOut to produce these vital parts of the exoskeleton ourselves. As we make our way through the exoskeleton from top to bottom, we will eventually reach the feet. And to us, this is one of the most important parts of the exoskeleton, as it's the first and only part to make contact with the ground. This year's foot plates feature a sensor that March has tried to implement for a long time, the pressure sole. Placed inside the sole of the foot, this sensor can measure the pressure the pilot puts onto the ground, and can therefore measure how balanced the exoskeleton actually is. If we measure stable values across the entire sole, it probably means our exoskeleton is in balance. But if we measure different values across the entire sole, it probably means we are losing our balance and we should compensate for that. Our pressure soles have a new design. They are simpler and optimized for our use. They can now measure the 3 phases of a footstep. First is the heel strike, then the toe off, and finally the leg swing. Using this information, we can know where we are in our walk and can balance the exoskeleton accordingly. So as we zoom out, we can see we've gone through the essentials of what creates an exoskeleton. The components we've highlighted will enable the March 8 to be the first self-balancing exoskeleton out of any of the March series. However, the components we've highlighted will be able to do nothing on their own. The March 8 has hundreds of wires running through custom-made electronic boards and cables all over the suit. And through changes we've made in this embedded and electrical architecture, our system is now 4 times as fast, speed that we can use to react even quicker to our changing environment and the world around us. The March 8 has more innovation than meets the eye though. Let's take a look at some of the changes we've made outside of the exoskeleton. We use a third and final new sensor, an IMU. Placed on the chest of the pilot and integrated into a user-friendly vest, this sensor can measure the orientation and tilt of the upper body of the pilot. When Koen, our pilot, leans a little too far to the left or to the right, our balance will change. And using the IMU, we can know this and compensate for it to stay in balance. And finally, looking at the top of the head of the pilot, you will see one of the strangest and most incredible pieces of March engineering made over the last few years. The EEG headset. The EEG headset measures the pilot's brainwaves and uses it as input for the exoskeleton. Or in simpler, perhaps cooler terms, using the headset, Koen can control the exo with just his brain. When Koen wears this and we place him in the exo, and he thinks of walking, the exo will start walking. Using the progress March 7 has made last year, we hope to improve this brain control even further. By removing interference from the signal, we will be able to use the headset not only to start walking, but also to stop walking, without using a single button. With the implementation of brain control and our self-balancing exoskeleton, we are one step closer to creating a free and unrestrained future for paraplegics worldwide. We will make it possible to have a beer by the bar again, or to have a nice lunch walk, hand in hand with your partner. That's something I would do in my ideal afternoon, and it's a possibility that we would like to give everyone. Besides the work I just touched upon, a lot of engineers have worked under the hood of the exoskeleton, and to dive deeper into these innovations, I'd like to invite my esteemed colleague from software, Sahand Waagmakers. Thank you.
balance is a task where the brain and body work extremely close together. From what we've just saw, our exo is certainly capable of moving, but we still need the software to tell it how to move. As this is normally something which our brain does mostly subconsciously, we would like our exo to be able to do the same, taking care of how to walk. So instead, our pilot Koen can focus on where to walk and anything else. During a normal walk, our body controls about 200 muscles at the same time. Of course, we barely think about it, but it's very easy to imagine how complex it is, what's actually going on. 200 muscles working together in intricate patterns, and all of this with barely even a single thought. This is, of course, something quite difficult to implement into your exoskeleton mechanically, so we can use the software along with the sensors and the motors to mimic this behavior instead. To be able to balance, we both need to take into account how our exoskeleton is standing at each point in time, its kinematics, and also how it is moving over time, what we call its dynamics. To achieve all of this, we've updated our software and implemented 3 big new features: model predictive control, hybrid zero dynamics, and torque control. And we believe that these 3 new features are the next step forward for March to go crutchless. Looking at all of you in the room, I would say there's around 500 of you. So let me ask you a question. How many people do you think you know? If you take into account school, work, friends, and family, I would say at least 50 is quite a safe guess. Now, what if those 50 people also know 50 other different people? And those 50 different people know 50 different people, and so on. If we were to display all these people on the slides over here, it would only take 6 of those steps to display all the people on the planet. From this, we can see how something with relatively few initial options, like 50, can result into an enormous amount of different outcomes in just a few steps. Now let's apply this to our exoskeleton. Let's say our exoskeleton has 50 different options, how it can move every second. And we would like to make a decision on how to move the exo based on how it's moving 6 seconds into the future. This is exactly what our new control method tries to do. Model predictive control, or MPC in short, tries to look into the future and predict each possible outcome of how it could walk. Of all these outcomes, we give them a score based on how well it's walking and how stable and balanced it's walking. And from all of these, we pick the one with the best score. Furthermore, by looking at all these different outcomes, we can also take into account situations where walking doesn't quite go as planned, where you need to respond quickly and fast, like maybe Wendell and his girlfriend tripping over a branch during their afternoon walk. This is what we call online balance in March. We create a walking pattern and constantly update it on the way as we deal with new, unexpected changes. Our model predictive controller does not have a fixed walking pattern. It instead constructs this every step of the way and in between. However, this strength is also where the method falls a bit short on its own. As we want to look at all these different outcomes every millisecond, it takes a huge amount of computational power to do this. There's 2 ways to fix this, of course. Either one, we simplify the kinematics and dynamics in this controller, or we increase the size of our computer, making the backpack maybe 5 to 10 times as large. Our mechanical engineers weren't quite happy with that choice though, so we just went with the first one instead. So, to deal with this, we've added a second method to go alongside this. Hybrid zero dynamics, or HZD in short. I'm not going to go quite into the details of how this works, as it is quite a lot to go through. So instead, let me just tell you what we're doing with it. Hybrid zero dynamics allows us to create a digital and general walking pattern which we can mathematically prove is self-balancing. This we do only once, and then we use that same walking pattern on the exo each time afterwards. We call this offline balance in March, where you only construct a walking pattern beforehand, which you know is self-balancing, and then use the same one each time from then on. By combining this solution, this general walking pattern, and our model predictive controller, we can reduce the amount of options we have to look through, as we can just look at the ones which closely resemble our general stable walking pattern. This in turn allows us to both increase the speed of our model predictive controller, as we have to look through a lot less different branches, and because we still use our model predictive controller, we can still deal with any unexpected changes along the way. Our next feature has a bit less to do with the walking patterns we walk in, but more so how the exo performs this walking pattern. It's based on the torque sensors mentioned earlier, and it's what we call torque control. To properly explain this, let me give you an example with this water bottle. Now, if I hold it in my right hand, there's two ways I can try and grab this with my left hand. The first one would be torque control, where I keep moving my left hand until I feel the force of the bottle pushing back. Then I slowly close my fingers around it. The other method, position control, would be where I first look where the bottle is in my hand and go to that exact location. Of course, when everything goes well, it looks a bit silly, as I'm just doing the same thing 2 times. However, if we don't quite know where this water bottle is, let's say I think it's a bit further away from me than it actually is, position control has some issues. When using position control, my hand would just keep going to that position, keep going until it pushes the bottle away. The way we use this in our exoskeleton is mostly during the foot strike. As we don't exactly know where the ground is, since this is only based on our sensor measurements, sometimes the foot can hit the ground just a bit earlier or just a bit later than expected. If this is the case, with torque control, we can ensure that we don't keep pushing into the ground, causing us to fall over. This, in turn, reduces the chance of falling, increases the robustness and the stability of our walking pattern. Now, we have gone through the 3 new features we're implementing this year in the software. A system which is able to take care of how to walk, so our pilot Koen can instead focus on where to walk and anything else with the rest of his body. A system which makes it a lot easier and stay self-balanced. And having gone through all of this, I would like to give the word back to Marilene.
It's the end of my day, and as I cycle back from Project March, I'd like to take a moment to reflect on and process everything that has happened today. And actually, that's what I would like to do with you now as well. So, walking without falling is really difficult to do, and recreating this behavior even more. In order to make sure we can, we've had to implement many changes which can be divided in 2 categories, mechanical and software. Mechanical-wise, we've implemented 3 new sensors: pressure soles, an IMU, and custom-made torque sensors. We also overhauled our linear joint design to be stronger and more robust. We redesigned the frame around the motors for manufacturing, reducing complexity while improving weight distribution. And finally, all our hardware communicates now 4 times as fast by our upgraded embedded system. Software-wise, we combine a method of online and offline balance using model predictive control and hybrid zero dynamics. The combination of these 2 creates walking patterns and then performs these walking patterns by using torque control. Overall, it's a year full of challenges, failing and standing up again. To make sure we accomplish each and every challenge, we have an amazing group of people supporting us. I would like to take this moment to thank all our partners who are essential for making sure we can build an exoskeleton. Supporting us by giving components, funding, and consultancy, you are the foundation we can build on and push the technology each year to a new level. Next to them, we have an extremely enthusiastic group of old March members who are always ready to jump in and guide us through our problems. It's amazing to see how many of you are still involved with the project and act as mentors to all of us. Finally, I would like to take a small moment to thank all our friends and family. Even though you may not see us as often as you did before, we want you to know that we are really thankful to have you as supporters. Gunnar, Sant, Wendel, and I have had the honor to present to you tonight, but we are just 4 people working in an incredible team. A team built of highly motivated, persistent, and kind people. It's a blessing to work with them every day, and to conclude this evening, I would like to introduce you to them. The mechanical department, Storm, Chris, Lieselot, Bas, Sanne, and Lika. The human department, Lisa and Tijn. The software department, Tessel, Joy, Jack, Sophie, Marco, Sahant, and Risk. The electrical and embedded system department, Joost, Tias, Lena, and Casper. The operations department, Puk, Marije, Sander, Jaron, and Tim. The management department, Leo, Gunnar, en Wendel. And last but not least, our pilot, Koen van Zeeland. Next to being colleagues, we have become a group of friends, and we enjoy each other's company. On Friday, we usually do that by having a drink together, and on that note, I would like to invite you for a drink at the foyer. We are the A-Team. We are Project March. Thank you all for coming. Whoop, 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 whoop.